In this video, we're going to introduce one of two graphical tools to help us make sense of compound probabilities or complex scenarios where we want to calculate a probability. And the first tool is called a tree diagram. So a tree diagram is a diagram, that shows branching for each of a series of choices. And there are two reasons why we build these. The first is that this helps us see what our sample space looks like. As statistical scenarios become more complex, this becomes more difficult to visualize in your head. So these graphs are going to make it easier to see all of the possible outcomes at the end of a series of choices. The other thing this does is this helps us with the multiplication rule and finding probabilities with the multiplication rule. And the how, we're going to do an example. So let's suppose we flip 3 coins. And I'm going to do my tree sideways, and we don't typically do them sideways, but that's okay. So here is my first choice. And when I flip a coin, I know I have 2 outcomes. I could have a heads, or I could have a tails. So that's my first choice. My first flip. I'm going to flip again. And I know for my next flip, I could have either gotten a heads first, and I get heads. Try that again. I get heads or tails. Or I could have flipped the tails first, and I get heads or tails. So that's my second flip. And then after my second flip, I'm going to flip again. Same division, heads and tails. Heads and tails. Heads and tails. And I'm sorry, it's getting a little messy. My hands are kind of shaky today. Heads and tails. I'm going to go in a different color. I'm going to write the probabilities. I know that for each flip, it's 50-50, 0.5, 0.5 for every branch, every choice, or every flip. Each flip, there's a 50-50 chance I'm going to get a heads or a tails. So from this, the first thing I see is I see my endpoints here. This is the end of my third choice. Third choice. So these right here must be the tail end or my sample space. So I'm going to read each branch and write out my sample space. Or try to, if my pen will cooperate. So reading along this first branch, I have heads, heads, heads. And then next branch, I have heads, heads, tails. Come on, pencil. And then I have heads, tails, heads. And then I have heads, tails, tails. And then moving down to the second branch this way, because this is all done, I get tails, heads, heads. I get tails, heads, tails. And then tails, tails, heads. And then tails, tails, tails. So I can now see I have 1, 2, 3, 4, 5, 6, 7, 8 outcomes. And I can use the size of the sample space and the items in the sample space to determine the likelihood that I get any number of heads or tails when I flip 3 coins. We're going to do one more example really quick that I think will be more helpful in terms of how we use this to calculate probability. So the next example says probability that a baby is born male in the US is 0.512. Certain family plans on having children until they have a boy or they have 3 children, whichever comes first. Construct a tree diagram for this scenario, then find the probability the family has at least 2 children. So I'm going to label this as boy and not boy for each birth. So they have the first child, and we can have a boy or a not boy. And I know the probability of having a boy is 0.512. So this is 0.4 or something. I want to say 488, but I'm going to double check to make sure I can do math in my head on a day when it's 109 degrees outside. Yeah, it is 488. Okay, good. I can still do math. And I look back at that family planning and it says, have a boy or have 3 children, whichever comes first. If they have a boy, they stop. That's an endpoint in my tree. If they didn't have a boy, they're going to have another child. So from this first birth, the not boy could be a boy or a not boy. And I know for this birth, those probabilities are the same. Probability for a boy is 0.512. Probability for not boy is 0.488. If they had a boy on the second go, they stop. Keep having children until they have a boy or they have 3 children, whichever comes first. Well, they had a boy before they had 3 children, they stop. If they had 2 births that were not boys, they're going to have a 3rd child. And that 3rd child could be a boy or a not boy. And again, those probabilities are going to look the same, 0.512 and 0.488. And at this point, the family stops. They were going to stop if they had 3 children or a boy, whichever came first. And in this case, they've had 3 kids regardless. And we want to find the probability that the family has at least 2 children. So I'm going to come through here in green and circle all of the endpoints in the table where the family has at least 2 children. So this is an endpoint, and they have 2 children. They have a not boy and a boy. This endpoint, they have more than 2 children, so that's at least 2 children, because they had a not boy, boy. And, stop. This one, they have at least 2 children. Not boy, not boy, they have 3 kids, which is at least 2. So to find this probability, I need to find these 3 probabilities and add them together. I have 2 children, where 1 is a boy. I have 3 children, 1 is a boy, or I have 3 children where none of them is a boy. So to do that, P at least 2 kids. I know it's those 3 branches, and to get the probability for each of those circled outcomes, I just multiply down the tree. So the probability of having a not boy and then a boy is just 0.488 times 512. So 0.488 times 0.512, and then plus, and then I have this outcome, which is 0.488, 0.488, 0.512. Or I have this outcome, which is 0.488, 0.488, 0.488. And 3 of them would be cubed. And that is a little bit easier to reason through with a probability tree than it is from scratch in my head. So I'm going to go ahead and plug this in my calculator, 0.488 times 0.512 plus 0.488, if I can type 0.488 squared times 0.512 plus 0.488 cubed. And when I do that, oddly enough, I get 0.488. And the question is, why does that make sense? And the answer is, this is a complete table with all of the possible outcomes for this family planning method, which means all of the probabilities in this table have to add up to 1. I have accounted for 3 of my 4 possible outcomes. 1 boy, 2 kids, 1 boy, 3 kids, 1 boy, no boys. Well, the only probability we haven't accounted for is this guy, and I know his probability is 0.512. 0.512 plus 0.488 equals 1. So that makes sense in terms of this representing this chunk of the table and the remaining chunk adding up to 1. All right, if you have any questions on how to draw a tree diagram or how to use it to evaluate the multiplication rule, feel free to send me an email or drop by office hours. Otherwise, I'll see you in the next video.